So, in our last class we have studied calculus of functions of several variables, then we have studied what is partial derivatives and we have calculated few sums where we have calculated partial derivatives. Now, based on that partial derivative and calculus of functions of several variables, we have the concept of homogeneous function. Now, what is this homogeneous function? This definition we can define it as an expression in two variables x, y, such that the degree of each term in it is same, say n, then it is said to be a homogeneous function. For example, if this is our f of x y, a naught x ki power n plus a1 x ki power n minus 1 into y plus a2 x ki power n minus 2 into y square and so on. Now, note degree of first term is n, degree of second term it is n minus 1 plus 1 again n, degree of third term n minus 2 plus 2 again n, degree of last term n. So, all the terms have same degree n, so we can say it is a homogeneous function. Homogeneous function simply means all the terms of a given f of x y of a given expression polynomial has to be same. If it is same, it is homogeneous. If it is not, it is not homogeneous, it is non-homogeneous. We can take some other example. Let us say we have f of x y 2x cube plus 3x square y plus y cube. Suppose this is f of x y. Note degree of first term 3, degree of second term 2 plus 1 3, degree of third term 3. So, it is homogeneous of degree 3, degree of this expression is 3. So, this is homogeneous since all the terms have same degree 3. So, we can say it is homogeneous of degree 3. We can also define this homogeneous function in a different way, that is a function u f of x y is said to be homogeneous of degree n if for any real number lambda f of lambda x lambda y equals, if it equals lambda raised to power n f of x y, then we say f of x y is homogeneous of degree n, where n is the power of lambda here. I will explain this definition with the help of example. Actually, we are using the definition for finding the degree. If we need to find the what degree this function is homogeneous of, if we have to calculate degree, we are always abiding this definition. The definition says if I multiply, this is my f of x y, if I multiply x with any real number lambda, that is lambda x, and y with any real number lambda, that is lambda y, and if on multiplying x and y with the real number lambda, we will be getting lambda power n with f of x y, then it is homogeneous of degree this power of degree n. Let us calculate some degrees so that it is well clear. Let us take first sum. F of x y is equal to ax square plus 2hxy plus by square. We need to find whether it is homogeneous or not, and if yes, what degree it is homogeneous of. So, using the second definition, multiply x with lambda, y with lambda. On multiplying x and y with lambda, I will be getting a, x will be now lambda x. I am replacing x with lambda x plus 2h, x is lambda x, y is lambda y plus b, y square, y is lambda y now. So, it is lambda y. What I have done is I have simply replaced x with lambda x, y with lambda y. So, wherever we are having x and y, we are just simply replacing it with lambda x and lambda y. Now, let us solve it out. After solving, we will be getting a, it is lambda square x square plus 2h, lambda into lambda will give me lambda square xy plus b lambda square y square. I can see lambda square is common throughout, so I can take lambda square common. I will be left with a x square plus 2h xy plus b y square. I will be left with this one, and we can notice it is f of xy, it is the same f of xy, so we can replace lambda square into f of xy. So yes, it is homogeneous, and it is homogeneous of degree 2. So here n is equal to 2, n stands for degree. We can also write rho is for degree, rho is equal to 2. Whatever the power of lambda we are getting, that is the degree of the homogeneous function. So it is homogeneous of degree 2. Let us take one more example. Let it be x tan inverse y by x. Let us find the degree of this. So, multiplying x with lambda x, y with lambda y. X will be replaced into lambda x, y will be replaced with lambda y, x will be lambda x. Lambda will be cancelled out. So, we are left with x tan inverse y by x, and we can notice it is the same f of xy. So, we can say it is lambda into f of xy. It is homogeneous, and the degree is the power of lambda, that is 1 here. So, here n is equal to 1. So, we can say it is homogeneous of degree 1. Let us take one more example. It is x upon x square plus y square raised to power 1 by 2. So, again multiply x with lambda x, multiply y with lambda y, we will get it is lambda x upon lambda square x square lambda square y square power half. What I have done is again replacing x with lambda x with lambda x, y with lambda y, I am getting this. So, in the numerator we have lambda x, in denominator we can take lambda square common, we are left with x square plus y square power half. This lambda will be cancelled out with this one. So, it will be 1 upon lambda root 1 by 2, we are left with x upon x square plus y square power 1 by 2. So, it is lambda power minus 1 by 2 into x upon x square plus y square whole power 1 by 2, and we can again note that lambda 1 by 2, this is our f of xy only, f of xy. So, we can say it is homogeneous of degree is the power of lambda, that is minus 1 by half. So, it is homogeneous of degree minus 1 by 2. So, this is how we are calculating degree of any homogeneous function, and based on this homogeneous function tomorrow in the next class we will be dealing with Euler's theorem, which is based on this homogeneous function only, and there we need to calculate this degree. So, from the next class we will be dealing with Euler's theorem.